In 2006, NASA launched an experimental project in Antarctica called the Antarctic Impulsive Transient Antenna, ANITA. Scientists sent a helium balloon carrying a radio antenna to an altitude of 37,000 meters, where it remained for a month. Antarctica, being far from human activity, has cold and dry air, which minimizes ground interference. Therefore, scientists hoped to capture high-energy particles from space, particularly high-energy neutrinos, in this pristine environment. However, after a month, when the data was examined, aside from occasional background noise, the results did not show the expected signals. NASA conducted 2 more experiments in 2009 and 2014, but the results remained disappointing. The breakthrough came in 2016. One day, while researchers were reviewing the old data, they discovered a peculiar signal among what was previously dismissed as noise. The characteristics of this signal indicated it was a high-energy tau neutrino. Although it fit within the standard model, the particle's behavior was illogical. It was moving not from the top down, as expected from space, but from the bottom up, from the ground towards the sky. What makes this strange? For high-energy neutrinos, there are no known sources on Earth, especially in Antarctica. Cosmic high-energy neutrinos typically originate from extreme astronomical events like supernova explosions or gamma-ray bursts. On Earth, the only significant sources of neutrinos are nuclear reactors, which is why many neutrino laboratories are located near nuclear power plants. However, the neutrinos produced by nuclear reactors are relatively low in energy and cannot be considered sources of these high-energy neutrinos. Another possibility is that these high-energy particles came from the other side of the Earth, possibly from a celestial body in the northern sky, and passed through the Earth to reach Antarctica, where they were detected. Since neutrinos are uncharged and have very little mass, or possibly no mass at all, they have an extraordinary ability to penetrate matter, making this scenario plausible. Scientists began investigating whether there was a high-energy neutrino source in that direction. To rule out equipment issues, they not only reviewed the data from the previous 2 ANITA experiments, but also collected 8 years of data from the IceCube Observatory. IceCube is a large neutrino detection station in Antarctica, consisting of over 5,000 detectors buried deep in the ice. Prior to this, IceCube had primarily detected ordinary neutrinos from the Sun. However, upon careful examination, researchers found high-energy neutrinos coming from the ground in both the IceCube data and the previous experiments. After thorough analysis, no high-energy neutrino source was found in the corresponding direction. With no source and no equipment issues, the only remaining explanation seemed to be the existence of new physics beyond the standard model. This shifted attention back to those mysterious high-energy particles. From their characteristics, these particles are consistent with those in the standard model, except for their reversed direction of motion. This led to a speculative idea. Could these particles be moving backward in time? Before dismissing this as far-fetched, the concept of time reversal isn't entirely baseless. Richard Feynman once proposed a similar idea. Feynman made significant contributions to modern quantum mechanics. He invented the Feynman path integral and Feynman diagrams, which are widely used in particle physics, and won the 1965 Nobel Prize in Physics for his work on quantum electrodynamics, QED. When pondering the nature of antimatter, Feynman once had a fascinating thought. Antimatter is remarkably similar to normal matter, differing only in certain quantum properties, such as having opposite charges, e.g. positrons. If both the sign of time and the sign of charge in the Dirac equation are reversed, the equation still holds. This implies that a positive particle can be seen as having positive time, while an antiparticle has negative time. Negative time suggests that the particle's time flows backward. In other words, the antiparticles we observe might actually be normal particles traveling backward in time. This idea offers a partial explanation for 2 enduring mysteries. Why is the universe dominated by matter? And where did all the antimatter from the Big Bang go? According to this hypothesis, the Big Bang might have produced two universes, one with time flowing forward, our universe, and another with time flowing backward, an antimatter universe. These two universes would be parallel, time-reversed counterparts, normally unrelated but occasionally revealing traces of each other, such as antiparticles or the high-energy neutrinos detected in Antarctica. But how plausible is this explanation? Calculations suggest that if such a scenario were real, the probability of detecting these phenomena would be extremely low, making it unlikely to observe them repeatedly. Moreover, while the idea of parallel universes is intriguing, it remains highly speculative. Proving the existence of parallel universes would require far more concrete evidence than these hints. Therefore, rather than invoking parallel universes, some scientists propose that these particles might be antineutrinos. However, this explanation also has issues. Like neutrinos, antineutrinos should have specific sources, and we have yet to identify any. This brings us back to the original problem, the missing source. Could the issue lie not with the neutrinos themselves, but with the detection methods? Currently, almost all neutrino detection methods are indirect. Although neutrinos have an extraordinary ability to penetrate matter, they can occasionally collide with atomic nuclei. When a neutrino interacts with the nucleus in a medium, it produces charged secondary particles. As these particles move through the medium, they generate a phenomenon called Cherenkov radiation, which can be detected by photomultiplier tubes. Japan's Super Kamiokande is a prime example of such a detector. Similarly, Antarctica's Ice Cube Underground Neutrino Observatory operate on similar principles. Thus, the high-energy neutrinos detected earlier were also observed through such indirect methods. Could some phenomenon related to these secondary particles be causing the anomalous data? Interestingly, some scientists have proposed exactly this. In a 2019 paper published in Physical Review Letters, the authors suggested that the secondary charged particles produced by these high-energy neutrinos might exhibit a phenomenon called geomagnetically induced coherent transition radiation, CTRGM. Under specific conditions, this radiation could significantly affect the electric fields generated by cosmic ray air showers, altering the expected pulse shapes or even reversing the polarity of the electric fields. This explanation is currently the most plausible one that does not violate the standard model. Other hypotheses, such as sterile neutrinos or exotic dark matter within the Earth, while slightly more grounded than the antimatter universe idea, still rely on too many assumptions. These explanations aren't necessarily wrong, but the current evidence is insufficient to support them. It's important to note that within the standard model of particle physics, neutrinos remain one of the most enigmatic fundamental particles. Regarding the Antarctic neutrino anomaly, all proposed explanations, including those involving secondary particles, are still under investigation. Determining the ultimate explanation will require more experimental data and deeper research in the future. As we continue to explore, we may eventually unravel the many mysteries surrounding neutrinos. If you want to explore more cosmic mysteries and unsolved enigmas, don't forget to subscribe to Studio One. See you next time.